So we are starting new, kind of a new topic within representation theory, but it's like one important notion of representation theory is unitary representations. And in general, how integration on compact groups are related to representations. It's a very rich, mathematically rich story, and I would like to discuss it just a little bit. Then we start with definition. So with a complex. So we work with complex representations just to have more instruments at our hands. Representation rho V of a Lie group G is called unitary if there exists, if there is an inner product on V such that, well, it's invariant with respect to an action of the group. So rho of G V, rho of G W equals V W for every V and W in V and G in G. So this definition, and you immediately can see why this is useful by the following proposition. Each unitary representation is completely reducible. And the proof is easy. So suppose that I have unitary representation, and suppose that I have sub-representation inside V, so sub-representation. Then I consider orthogonal complement with respect to the form, the inner product that I have on V, right? So this is inner product that I have. Yeah, so by the way, does everybody understand what is inner product?
So it's a very linear form which is symmetric, non-degenerate.
Yes. Yes, well, we have complex representation, so it's Hermitian.
Yeah, like it's half linear, I say.
Yes, and also, yes, it's non-degenerate and positive definite, right? So if you have two, if you take V and W equals to V, right, then V with itself gives me positive numbers if v is not 0. If it's 0, then it's 0. Okay, just to check that we're on the same page. Very well, then. So what is this then? We have, so this is all vectors, I don't know, W, or, okay, W lives in here, so U in V, such that U with V with W, right, equals to 0 for every W from W. So this is by definition what is orthogonal complement, and since the form is non-degenerate, it's just some elementary linear algebra is that the direct sum is V. Moreover, I claim that W orthogonal is subrepresentation. Well, we can check it, right? So if I have V, okay, suppose that I have U inside here, right? Then I act by row of G, and I would like to see that this is also inside, right? So I take any W, compute my inner product. So this is by invariance is this. Right? And this belongs to W. But U is from W orthogonal, so therefore this is 0. So therefore row of G U is also from W orthogonal. So we proved. So if I have subrepresentation, then I have complement subspace, which is also subrepresentation, which by definition means that it's completely reducible. And now we would like to focus on compact Lie groups G, and say that every representation of compact Lie group is actually unitary. So there is form which is invariant. So theorem that we are going to prove is that any complex representation of a compact Lie group is unitary and hence completely reducible. All right. Okay, so the proof will take a while because we'll need to discuss a couple of things. So first of all, I would like to recall what is pullback of differential forms. Okay, I will need it. Okay, so for any smooth map between two manifolds x and y, f, it goes from x to y, we define map f star, upper star, which goes from one forms on a y to one forms on x. How do we do this? So we take one form on y. And if we act by f star, I will get one form in X by the following rule. So, I need to choose a point. So one form, right, it gives me linear functional, right, on tangent on a tangent space at each point. So I have a fixed point, and this thing becomes a linear functional on tangent on a tangent space to X, right? Since this is a form on X, this is a form in here. So I choose a vector in here, and I just need to give you a recipe how this should act in here, right? This should give me some just a complex number, right? All right, or rather real number, because group is we think of group as a real group, and a representation is complex representation, right? So it's compacted as real group. You can say that okay, it's complex, but and compact, but then it's nothing interesting because we learned then it's the abelian, right? I learned on seminars. So yes, and I just define it like this. So I have eta f of x. So this guy eats vector, right, from the tangent space of y at this point f of x, right? And I give him this vector by as follows. So this is vector that lives in T f of x, y. All right. So this is just recall what's going on, and then we can take this definition and extend f star to omega k to k forms. Well, it's just most natural way to do this. So I take so if I have k1 forms, I consider which of them, right? Then I will just take f star of eta 1, which f star eta 2, and so on, which f star eta k. And of course, I can also define it just for smooth functions on y and x. So if I take k equals 0, right, 0 forms are kind of smooth functions. And we just can define f star that goes from c infinity of y to c infinity of x. You just compose your map. It's just even easier. You just take your map from here and compose it with f, and that's it. So then we define f star f. This is a map in here. At x is just f of x. That's it. All right. Then if we define it like this, then we actually can say the following. If I have f star of f times some form omega, and this lives in C infinity of my x, and this is some form. Then I have just f star. This is f star omega, f star f. This is again some function times some form. So how do you make a change of variables in a form with some coefficient which is a function, right, on x? So you change coefficient in your function and then change coefficient in the form. Nothing else is written. Okay. And then let's go back to this setup where my manifold is G, both actually, x and y and G is G, and f will be just left action by some element in G. But first what I need to fix some element in here, in the top external 10 to the power of G star. So so you should think of it as a value of some form, like top form at identity. And then we would like to, take this and extend it to the whole group just by left action. Okay, n here is dimension of G, and well, G is of course the Lie algebra of the Lie group G, and then I would like to define omega tilde. It's an n form on G. By the following. So I just need to, again, to take omega tilde. This should eat some vector from the tangent space at point G, right? So V is from T, G, G. And I just define it as omega E tilde, but then I need to move this vector back to tangent space at identity, right? So I use DL G inverse, well, at point G of V. That's how I move vectors. That's how I move this form to the whole group G by left action. Okay. So since this is not only smooth map but diffeomorphism, right? I actually have nowhere vanishing form. At no point it is not zero. At any point it's not zero. And also I can see that it is left invariant. So let's check it. So I would like to compute LG star. So this is multiplication from the left by the element G. And then I put star in the sense that I described here. I apply to omega tilde. I would like to see that it is just tilde. It is just omega tilde. So I need to put and compute this at point H and act on a vector V that lives, so V here lives in T, H, G, right? this is by what we see here, according to what I defined, is omega tilde GH of DLGV. So I shift this vector, right, by the left action to GH and compute its value acting by this functional. And this is at point H. All right. But then this I can write now and use definition of W tilde G, right? Then I use this now. So I will have W tilde E. And then of DL GH inverse DL. I'm not putting where I put differentials. It's you can recover it if you wish. What's important is what stays here. DLG of V. So like this. Or maybe yeah, okay. So then I can compose these two, and this will give me G. So GH inverse times G is just H inverse, right? So it's H inverse G inverse times G. So it's just H inverse. So I guess I get W tilde E DL H inverse of V. But this is just by definition omega H, omega tilde H at V. So we checked. So therefore, right, LG star omega. So omega is left invariant form, n form, and omega tilde. Okay, so I'm writing omega tilde for now because I would like to. I chose some element. Of course, I would like it to be not zero. Otherwise, this all makes no sense, right? And so I chose some non-zero element. I would like to renormalize it so that integral over the group becomes just 1. That's why I'm writing omega tilde for now. Okay. Yes, so I think here I lied to you a little bit because this is form of degree n and doesn't eat just one vector, right? It is n vectors, actually, right? So, but I can do it, so I can replace this with, yes.
Nothing changes. Maybe even if you take like one form, no, by linearity.
Yeah, but I really want to fix some n form, right? And then, well, then this is just v1, and this is just all the same, right? I just need to replace just this one vector with the same formulas, right? Like this, right? And in principle, I would just replace v. So this is vi, and I can right now v bar is just a bunch of vectors. v1, vn, and by this I mean that I plug this in like these vectors inside, and by this I mean really the following tuple. Okay, and now I can just put bars everywhere, and this will make sense. Okay, just to make sure that everything's correct. All right. So since the left action is actually diffeomorphism, right? So we actually have a very good form in the sense that it defines an orientation on G, right? It does not vanish at any point, right? Since we took something that is not zero in the beginning, it cannot vanish anywhere. So form omega tilde defines an orientation on G and with this orientation we now can talk about integration on our manifold, which is a G, right?
So orientation means like that we have a non-degenerate form.
Yes, non-degenerate global form. And so basically it just chooses, so if you go to coordinates, right? In coordinates it's like dx1 wedge dx2, it gives you some order on dx, right? And so each order of coordinates has there are two classes of orders, right? They changes. So they if you put a form with a corresponding order and try to replace it to get your form in these coordinates, you get either plus or minus, right? So the coordinates that are plus, they are all kind of consistent and gives you consistent choice of bases at every point that gives orientation. So that's how it works. But this is some differential geometry, of course. But okay, it's important to understand here. Anyways, it's just sometimes orientation, just two ways to define orientation, right? It's just either by consistent atlas, right, such that the transformation, Jacobian of the transformation is positive. Or I just can give you global non-vanishing top form. Is also, but another way to do this. All right. So therefore, which defines well, just what is integral over some form eta, so for any eta from this. So another fact from differential geometry, which we will just take as a prerequisite for our discussion, is that since G is compact, integral over omega of G is
What is the degree of the
dimension of G. So, well, n, right? So since I already fixed this notation, that n is dimension of G. Okay. So, all right. I claim that this is this thing is infinite. Finite. Sorry. Less than infinity. It just follows from the fact that G is compact. So therefore, we just can take this number and normalize it our omega tilde. So we define omega to be 1 over this integral omega tilde. So then we just have integral over g of this omega is 1.
But why this number is not 0 in the denominator?
Because omega is non-degenerate at every point. It's actually positive, since it gives us, since our orientation that we chose is actually the orientation that that is given by omega tilde, this actually is positive, and we can define. So you kind of need to recall what was going on. So you put your charts, and every chart is just dx due to something, and then you take like a partition of unity, and this gives you like what is an integral here. But at every chart is just a positive number. All right. So I claim that the following happens. Integral, if I compute, if I have my form omega, and I compute integral with respect to this form, but also I multiply it by Lg star f, where f is some function on g. This is just the same as integral f omega over g for all f in C infinity g. Okay.
Just our last invariance, right?
Yes. So we have in a sense what's called like left invariant measure on a group. Yes. So let's prove. I mean the claim. So proof of claim. Again, we will use some knowledge from general theory of integration on manifolds. And this general theory says that if f is orientation preserving diffeomorphism, then the following is true. If I integrate over this form, this is okay. Let me just put omega here, right? Doesn't depend on which particular form I put in here, right? It's not necessarily this. Maybe. Okay. Let me have some eta for any eta in omega and g. All right. So therefore, we can apply this. LG is actually orientation preserving diffeomorphism. Well, just because that's how we, because omega is invariant with respect to left action, right? So if I shift by left action, I get again omega, which again, so So LG star omega gives me the same orientation as omega. So this is orientation preserving diffu. So therefore, I can apply this and have LG star F omega. So I start with left hand side there. Then I apply this. So it's over G over G. So I would like to apply LG inverse star to the, so this is, the whole thing is some form, right? And I apply LG star to it and induce this. So I'll have LG star F omega. But then remember our formula that F star applied to F small omega is F star of F small times F star of omega. So this is integral over G. And well, this composed to this x union F is just F. So this is F L G inverse star applied to omega, but omega is left invariant, so therefore we have F omega. Okay. So let me now put it as a remark, since there is very well-known terminology. We cannot go around it, but one needs, I guess, more some more measure theory and I don't know, some differential geometry to see that actually this is again not about Lie groups, but rather about smooth manifolds. So if I have a form like this, then there exists measure let's denote it as mu on G such that integral over G of F omega is integral over G F of G d mu of G. And this measure is actually left invariant in well, so if you take a set, compute a measure of it, apply left action of by some element, then the measure of what you get is the same in this sense. But we just work with forms rather. But still, and so this measure is called the Haar measure. So measure mu, so definition. Mu is called the Haar measure. And so we will actually write this, right? But we know that it's just the same as this. We don't want to go deep into like measure theory. Rather think about just integral with respect to some form.
But it's constructed
But it's the same.
in the same way as the Lebesgue measure, for example. But we define it first
Yeah.
with semi-rings and then extend it to high, like to more reach sets.
So you're asking how to construct what
What is the construction?
What is the construction? I think I cannot. So it's so the heart of it is Reed's representation theorem, and this is some theorem that is this is needed to be proven, and then just a consequence of it. So if you're interested, you can Google it and see how it's proved. Okay.
A brief question.
Yeah.
Why LG minus 1 preserve the orientation?
It just doesn't really matter which element stays here. So I'm saying that. So my argument is that take any h. It might be G inverse, might be G. So this is true that we. So therefore, orientation defined by omega is the same as orientation defined by by this form, which basically what it means for this diffeom to be orientation preserving. Okay. Very well. But this type of writing will be sometimes more useful for us because we have, in some sense, the argument here, like a variable of integration, which is hidden somewhere here, right? So it's kind of more explicit in a way. But remember, we are trying to prove unitarity of any representation of a complex group. So now we can construct actually an inner product. All right, so I can actually now take some inner product on V. Well, V is a complex space. I just can take like a standard Hermitian form there. Just, I don't know, fix some bases and just dot product in a sense, right? But with conjugation on the second factor. So take B V1, V2 to be this is just some inner product on our representation V. Then we can construct invariant inner product B tilde of V1, V2, which is integral over G, B, G, V1, G, V2, d mu of G. And by the way, we shouldn't worry too much that integral diverges or something like this, or because our group is compact. And like this form has no like singularities or whatever on this group. So kind of we are safe in this. All right. Then by the claim, which I erased, unfortunately, but we can recover it. So let me just first put the following on board. Then by claim, B tilde V1 V2 is an invariant inner product. Right? It's just because, well, I take B tilde, right, multiply by both V1 and V2 by H, by some H in a group, not multiple, by act on both. This is integral over G, B, H, G1, H, G, V1, H, G, V2 d mu of G, right? But this thing is some function of G, right? To which I applied LH, right? So if I just say that I have a function f of G, which is b of G v1, G v2. So I fix my v1 and v2. Then what's written here is just integral over G LG LH, sorry, star applied to f omega. But we checked that this is the same as integral over G f omega, which is just b tilde of v1 v2. So this is just b tilde of v1 v2. So indeed, any representation of so this is the end of the proof of theorem. So we've constructed a form b tilde on any finite dimensional complex representation V over a compact group. Okay, so now let's see. We for free we get some complete reducibility of all finite dimensional representations of SL2C. So let's see why is that true. Any finite dimensional representation of SL2C is completely reducible. Well, proof goes like this. So we actually have that SL2C is complexification of SU2 right? So in particular, any complex representation finite dimensional of this is complex representation of this, and the other way around. So we actually have the following correspondences. So we have representations, or rather isomorphism classes of finite dimensional, of course, representations of SL2C, and complex finite dimensional representations of SU2 Lie algebra.
So this is just the effect of our complexification, yes?
Yes.
So those the first.
So this is because of this. And also all this corresponds to complex representations of Lie group SU2. This is because what? SU2 is simply connected.
P1 is trivial, right?
Yes. And moreover, under these correspondences, completely reducible representation goes to completely reducible representation. So every representation here is completely reducible because SU2 is compact Lie group. right? So therefore, every representation here is also completely reducible. So how to put it on board? So SU2 is compact. And under these correspondences, completely reducible goes to completely reducible. That's it. That proves the corollary. Okay.
Is it also true for infinite dimensional representation? Since you have
No, it's not true for infinite dimensional representation.
where we used that our representation is finite dimensional?
Just to say that we have representation of a group. So by definition, representation of group is a homomorphism between Lie groups. And we don't study yes, infinite dimensional Lie groups.
No, just the effect of our vector space is finite dimensional.
Yeah, but it actually it's not true that for infinite dimensional representations. And one particular example of this is in the seminar today. So since we have this integration on our compact Lie group, we can use it more. And
The thing is that we would need a kind of infinite dimensional theorem.
yeah. So it's just another theory.
Yeah.
I mean, infinite dimensional Lie algebras are already, hard enough to study, even without going to groups. But I mean, we will see next semester. So there's already a lot of interesting. If we even forget about groups and just think about what we can do about what infinite dimensional Lie algebras can we study. All right. So, right. So, by the way, the complete reducibility of representations of SL2 can be proved in various ways. One is more algebraic, if we don't use groups, using at the center of universal enveloping algebra. And the one is the more analytic that we used here. And both can be generalized to any simple Lie algebras. Both proofs, semi-simple. So we'll see which. So plan to generalize this one, but we'll see how we'll end up. All right. So we actually can now take our integration and define an inner product on smooth functions. So we define an inner product on C infinity G, but I also would like them to these are smooth functions but complex valued. Okay, since I'm now I will call about orthogonality of elements of a matrix of representations, and since representations are complex, I would like my smooth functions to be complex valued. So this is why I put C in here.
Can't you just say an analytic?
No, analytic is too much for me. They are smooth as real functions, but they take very soon.
No serious.
Yeah, so you see, my compact group might be just real group. There's no, so there might be no analytic structure on G to carry. Okay. So I define by the following. I have F1, F2. So these are elements in here. By definition, this is integral over G, F1 of G, F2 of G, conjugated, d mu of G. So because I have conjugation here, right? If I take F1 and F2, right, I will have something positive in here, right? Because at every point I will get some positive number. So this in particular, this is why I can say that inner product, positive definite. All right, and now we can formulate the following theorem. So let me fix again this G for us, it's still compact Lie group. So let me fix two representations V and W. So these are two irreducible representations of my Lie group G. I would also like them to be non-isomorphic. And let me define the following elements in here. So rho ij, so these are of V. So my rho ij of V of G, right? B, sorry. The matrix of corresponding to rho V of G in some in an orthonormal basis of V. Okay, it's just notation. So I have two representations, and this, and also let me introduce the same notation for W as well. So if I put W here, then rho ij of W are matrix elements of this matrix where I replace V with W. In some orthonormal basis that I fix in W. Okay. Then each rho ijv or rho ijw is an element in here, right? So it's a function on G, a smooth function on G, complex valued. So therefore I can compute an inner product of these things. So the statement of the theorem is then the following. So then first of all, rho ij v rho ab w inner product is 0. For every I j from 1 to dimension of v, and for every a b from 1 to dimension of w. And 2 is that if I take matrix elements of the same representation, say v, then the result is the following: delta ik delta jl divided by the dimension of v.
So we have some orthogonality.
Yes, so they are orthogonal, and we actually know what to do to normalize them, right? So we know everything, right? So this is basically a Schur's lemma. We just need to find corresponding intertwiner. So proof. You see, it even looks like Schur lemma, right? If we have the same representation, something. If not, then 0.
What is the inner product here? It's just the multiplication of 2.
This one. So this rho ij is a v. It is actually in C infinity of GC. So this parenthesis is this parenthesis. All right. Okay, let me fix. So let VI and I don't know W A be orthonormal basis in V and W respectively. Well, my group is compact, so therefore they both are unitary, so I can fix inner product on V, fix inner product on W, and so this is some orthonormal basis with respect to this inner product that I fixed. Okay. Consider, so for each A from 1 to dimension of W and I from 1 to dimension of V, consider a linear map EAI is a map from V to W. It sends VI to WA. So it's a rectangular matrix with one just on one place. Which one you figure out yourself. I throw an A column on the other way around. I don't know. Just need to be. And so it just sends VI to WA and VJ where j is not equal to I, to 0. All right. So I would like to define, then consider the following map, phi ai. So this is a map again from V to W, and this is I just take my EAI and integrate, conjugate it and integrate. So EAI rho W of G, rho V of G inverse, d mu of G. So this is a matrix that acts in V. Then I go from V to W, and then I twist it by an action of G in W. And then integrate with respect to Haar measure over G. So I claim that this is an intertwiner of G action. So it commutes with an action. Let's check. So claim is that phi ai is, well, what we call homomorphism of representations. Well, indeed, I just need to take phi ai, and I can write rho vh inverse, so conjugate it in some sense, right? Rho w of h. So if this is the same as phi ai, then it's a homomorphism of representations, right? Then it kind of commutes with action. Not kind of, commutes, right? So okay, we just need to integrate. So we just plug definition of phi, right? So I will have EAI rho v of G inverse, but the integral is linear, so it commutes with linear maps. So so this conjugation is just some linear thing that I put inside the integral. So I will have rho v of h inverse, and here I will have rho w of G, rho w of h, and d mu of G. Okay, but this is then integral of rho w of hg e a I rho v of hg inverse, right? D mu of G. Then I use left invariance of Haar measure, and I can now write that this is integral over G of rho w of G e a I rho v of G inverse d mu of G. So this is left invariance. But this is the same as phi ai, right? So we proved it, the claim. Very well. So what's left? So by Schur's lemma, phi ai should be 0, right? I wanted V and W to be non-isomorphic representations, and this is homomorphism of two non-isomorphic irreducible representations. So therefore it's 0. and therefore, so phi AI, it's a linear map, right, from V to W. But I can consider it as a matrix because I already fixed bases in V and W, right? I can consider corresponding matrix. So I claim that in my basis VI W A, so phi A I is a matrix with jth bth, so j bth element given by the following. So integral rho b a of g and rho j I. So here W, here V, G inverse d mu of G. So again, if you just look, so this is in, you just need to do it yourself if you don't believe me, right? So this is in basis V and W is some matrix. So I claim that j-bth element of this matrix looks like this. Okay, some elementary manipulations with matrices. But then this, so this integral over G, I can replace, so this thing now. And I'm going to use the following, that rho ji vg inverse is the same as rho I j vg bar. So this is because I chose orthonormal basis. So this is an element of my matrix in orthonormal basis. Moreover, this matrix is unitary. So by definition, my inner product is invariant with respect to the action of rho of G. So this matrix should be unitary. And this is just a condition for this matrix to be unitary. And I am using it here, so I get rho B A W rho ij of G transposed V d mu of G. But this is just what we need. This rho. So maybe in another direction, right? So I have rho, so this is doesn't really matter. So what here exactly is rho BAW, rho IJV, right? So what's written here is just a scalar product, inner product of these two things as functions on G. Just by definition of our inner product. But we know that phi AI is 0. So therefore, all elements of this matrix are 0. So therefore, this is 0. And we proved 1. So let's prove 2. Proof of part 2 goes like this. We just need to repeat the whole argument that we just did. So repeat the above argument. we just replace W with V, and basis WA we just replace with VI. So just take the same basis. So now AIA is actually a square matrix, right, with 1 on the intersection of ith row and ith column, or the other way around with columns and rows. All right. So we actually, and this, so we can define phi ki the same way we did there. It now becomes integral of g rho v g e k I, right? So, and here v again, g inverse d mu of g. And the same computation says that phi ki is homomorphism of representations. So it's a phi is from V to V now, and it commutes with action of G on V. So then by Schur lemma, we know that phi ki should be some constant C ki times identity on V, right? So we just need to compute this constant. Moreover, we can use the same thing as there. So this is some matrix in the basis corresponding to basis Vi, right? And so I can now write Ljth element of this matrix. And this will be exactly rho Lk V of G rho Ji of G inverse V d mu of G integral over G, and this is Ljth element of matrix phi ki. But this equals to this. What is our Ljth element in this matrix? Yes, so CKI times delta Lj. So this equals to CKI delta Lj. So we just need now to compute CKI. We'll use trace for that. Okay, this we can erase now. So we're proving this, right? So my CIK should be delta IK over dimension of V. That's what we expect. Okay, so CKI, it's 1 over dimension V. I can compute trace of phi ki, right? So I can put trace on both sides, right? On the right side, so this is just CKI, 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 like this diagonal matrix. So I sum this up, I will get dimension V times CKI. On the left, I will have trace. So I divide by dimension of V, I get this. Okay. On the other hand, what is this thing? So trace is again something linear, so I can put it inside integral in the definition of phi ki. So I will have rho, so trace rho v g e ki rho v of g inverse d mu of g. Right? So trace of conjugated matrix is the same as trace of original one, so it's the same as trace of EKI. The trace of EKI does not depend on G at all, so I can move it outside of integral, and I will have integral of over G of d mu of G, which is 1, right? So actually what I get here is just trace of EKI over dimension of V times integral over d mu of G. But this one we chose our harm measure in such a way that this is 1. So this is, but what is trace of EKI? Delta Ki. Delta Ki. So we have that this is delta Ki over dimension of V. So we actually almost proved 1, right? 2. So in 2 I have rho ij yes. So let me see. Just to match this thing. So I have. So again, I have this integral rho Lk, right? V of G rho Ji. So now I take. No, let me not write it down one more time. So this, again, by unitarity, I erase inverse here. I replace I and j and put bar. This is by unitarity. So I will get rho ij v of G bar d mu of G, right? And so ij. So on one hand, we computed that this is delta Ki delta Lj divided by dimension of V, right? So Cky I just can put in here, right? And so this thing, which is the same as this, equals to this. On the other hand, this is rho Lk inner product with rho ij V. So it's actually the same as. So if I replace the two, I will need to get conjugation, right? But this is just real number. So conjugation means nothing. So this computation proves me 2.
Sorry, but in the formula we have k on the first index, but here we have the second on the second place.
So maybe. So I need rho I. So here it looks good because right. So I need really them to be the same. So let's check ikjl. Yes. So this one, I think, no mistake. This one, so I need to compare with this one. IK, JL. Wait, I think it's the same.
No, when we switch them, oh, in the last row, when we switch row LK and row IJ, we have row IJ as in the top, and row LK, but not row KL.
Well, you can name L to be K and K to be L. Delta does not see that, right?
These are compared to chronically switch.
So they just, they will be replaced. You can interchange delta connectors. Yeah, so I have just this commute. These are two numbers, right? So no.
Yes.
Yeah, I can just replace them, and this will be the same. Okay. Right. So yes, this is a good place to stop. So we proved the orthogonality of matrix elements, and next time we'll talk about orthogonality of characters and introduce characters.